We were looking at this question related to properties of expectations, where we looked at part A and B earlier. We want to now look at part C and part D. Now, if you look at the difference between part C and part C asks us to find expected value of x squared plus y squared, and part D asks us to find expected value of x plus y squared. So now starting with part C, we want to find expected value of x squared plus y squared. Here we'll use the fact that expectation is a linear operator like we used in part A. Since expectation is a linear operator, and recall what do you mean by linear operator? Linearity means that the expectation operator can go inside summation. So linearity means that the expectation operator can go inside summation. Which means expectation of sum is sum of expectation. And constant multiples can come out. Right, so here we'll use the fact that expectation is a linear operator, so expectation of sum is just sum of expectation. So because of the fact that expectation is a linear operator, so we can take this expectation operator inside summation, write this expectation of sum as the sum of expectation. So we can do this because expectation is a linear operator. This is similar to how in part A, we wrote expected value of x plus y is expected value of x plus expected value of y. Now what we do is we need expected value of x squared and expected value of y squared, right? We now need expected value of x squared and expected value of y squared. Now for expected value of x squared, we'll use the fact that we know that x is a geometric random variable. It's given to us with parameter p. P represents its probability of success. Where we know that expected value for geometric random variable is 1 by its parameter p, and variance of a geometric random variable is 1 minus p by p square, right? Now, since variance we know can be found as expected value of x squared minus expected value of x whole square. So we can find expected value of x squared as simply variance of x plus expected value of x squared is variance of x plus expected value of x whole square, right? Which in this case is just going to be 1 minus p divided by p square, which is variance of x, plus expected value of x whole square is just going to be plus 1 by p square. And this would just be, then if you just simplify this, this would just turn out to be 2 minus p. Right, so if we simplify this, this would turn out to be 2 minus p by p square, right? So here the idea is that expected value of x square can easily be calculated if you know variance of x. Expected value of x square can be easily calculated if you know variance of x and expected value of x, right? So we needed expected value of x squared. We know x is a geometric random variable with this expected value and variance. So using these, we can easily find expected value of x squared. Right, so now moving on to expected value of y squared. We know y is a binomial random variable with two parameters and represents a number tiles. R is the probability of success with this binomial random variable. The expected value of this binomial random variable is just the product of its two parameters n r. And the variance of this binomial random variable is n times r times 1 minus r, right? So again, we know the variance of y is just going to be expected value of y square minus expected value of y whole square. So based on this, we can find expected value y square as variance y. Like we said, once you know variance, unexpected value of a random variable, it's very easy to find expected value of its square using the variance and its expected value. So if it's nr1 minus r plus nr square, now if we just factor out an nr here, this becomes 1 minus r plus nr, right? So we know this is, so now we have found this, now it's very simple. So we found expected value of x1, expected value y square. So now we can just simply write, oh sorry, so expected value of x square plus y square, we know using the fact that expectation is a linear operator, we can write this expectation as sum of expectation, and we just found that expected value of x square is 2 minus p by p square, and expected value y square is plus nr 1 minus r plus nr. Right, so in this way we found expected value of x square plus y square. We first use the property that expectation is a linear operator to write expected value of x square plus y square as expected value of x square plus expected value y square. And then to find each of these expected value of x square and expected value y square, we basically found it using, we were able to easily find it because we knew the variance and expected value of each of these random variables. Now let's look at part D. Part D is expected value of x plus y squared. Now to do this, we'll first expand expected value. We'll first expand x plus y square using a plus b square, right? So we can write expected value of x plus y square as expected value. If I expand this using a plus b square, what is a plus b square? It's a square plus b square plus 2ab. So I will use this identity. So this will become expected value of x square plus y square plus 2xy, right? Now, since expectation is a linear operator, again, we're using the fact that expectation is a linear operator, which means that expectation can go inside summation and constant multiples can come out. So this is a very important property of expectation, which allows expectation to go inside summations and for constant multiples to come out. So again, using this property, so then we can write expected value of x plus y square as expected value of x square plus expected value of y square plus 2 expected value of xy, right? Again, because expectation is a linear operator, we can write this expectation as sum of expectation, and we can take out this constant multiple 2 out. Now, this we just found to be 2 minus p by p squared from part C. This we just found, right? This we just again found in part C. We just found this to be nr, right? 1 minus r plus nr again from part C. And this we found in part B, where this was the only place we've used the fact that x and y are independent, right? Because expectation is a linear operator, so expectation can always coincide summation regardless of whether you have independence or not. But expectation of product is only product of expectation and independence holds. We discussed this in the earlier part, right? So this we found from part B. From part B, we found expected value of x, y to essentially be, so this part only and not the two, so nr by p from part. So so we can write expected value of x plus y square is expected value of x which is 2 minus p by p square plus expected value y square is nr 1 minus r plus nr, and then plus 2nr by, so this was pretty simple. We just apply the fact that we just use the fact first we had to expand expected value of x plus y square, then we use the fact that expectation is a linear operator, then each of these individual expectations we already had in earlier parts. So something to very important note for part D is a warning. Now a warning for part D is that expected value of x plus y square is not the same as expected value, sorry, is not the same as expected value of x plus expected value y whole square. This is not true, right? ठीक है, so you cannot say कि expected value of x plus y whole square is the same as expected value of x plus expected value of y whole square. This is not true. Expectation cannot go inside a non-linear function like square, right? Main property is that expectation is a linear operator, and linearity lets expectation go inside sums. It can go inside sums, right? Like in part A, we could write expected value of x plus y is expected value of x plus expected value y. In part C, we could write expected value of x squared plus y squared, right? So it can go inside these sums, right? You can write as expected value of x squared plus expected value of y squared. So it can go inside sums and scalar multiples. So it can go inside sums and scalar multiples can come out, but sums and scalar multiples to come out, but right? So we're by go inside sums, we mean के expected value of x plus y, expected value of x plus expected value y, and scalar multiples can come out, which basically means expected value of ax can be written as a expected value of x, just like the 2 in part C we brought outside of expected value of 2xy. But not inside, expectation cannot go inside non-linear functions like the square, but not inside non-linear functions like squares, right? So basically, so what it means is that it cannot go inside non-linear, not inside, cannot go inside non-linear functions like squares, right? Which is why, like we just said, expected value of x plus y whole square, so it cannot go inside this non-linear function like square. You can't say that the expectation can go inside this non-linear function. So it cannot go inside the square, right? And you can't write this as expected value of x plus expected value y. Expectation cannot go inside the square. It can go inside some constant multiples can come out, but it can't go inside the square like this. So in part D, so you cannot do this in part D. Similarly, in part C, you can't do it, right? Right. So basically, so in part D, cannot do this, right? So this cannot be done in part D. Similarly, in part B, so cannot similarly, you cannot do this, right? This is also not true, right? You can't say expected value of x square is not the same as expected value of x whole square. Right? It cannot go inside the square. Similarly, right? So it cannot go inside this square, right? Similarly, you can't say expected value y square. It's not the same as expected value y whole square because expectation cannot go inside the square, right? Here also it cannot go inside the square and we can't write its expected value of x plus y whole square. It cannot go inside the square and we can't write its expected value of x whole square, right? So that's why in part C, when we were finding expected value of x square and expected value of y square, we could not just take the expected value of x and square it or take the expected value of y and square it because expectation cannot go inside non-linear functions like squares, which is why we use the variance of x and expected value of x to calculate it. Similarly, in part D, you cannot, that's the reason we had to expand it in part D because expectation cannot go inside the square.